Welcome to the session on sequences and series, geometric sequences. The objectives for this session are to find the nth term of a geometric sequence. A geometric sequence has a common ratio between consecutive terms. The formula for the nth term of a geometric sequence is u subscript n equals a times r to the power n minus 1. Here, u subscript n is the nth term of the sequence, a is the first term, and r is the common ratio. Let's now take a look at some examples. An example of an increasing geometric sequence is 3, 12, 48, 192, and so on. This is a geometric sequence because each consecutive term is multiplied by the same number each time. So, 3 times 4 is 12, 12 times 4 is 48, and 48 times 4 is 192. An example of a decreasing geometric sequence is a third, a sixth, a 12th, and 1 over 24, and so on. This is because it's multiplied by the same number each time. So, again, we've multiplied a third by a half to give a sixth. We've multiplied a sixth by a half to give a 12th. And we've multiplied a 12th by a half to give a 1 over 24. When the common ratio r has mod r less than 1, the sequence tends to a certain value. This is the limit of the sequence. An example of an alternating geometric sequence is 3, minus 9, 27, and minus 81. The signs, as you will notice, are alternating, hence the name. Of course, this is a geometric sequence because we're multiplying by the same number each time. The first term, 3, has been multiplied by minus 3 to give minus 9. Minus 9 has been multiplied by minus 3 to give 27, and 27 again has been multiplied by minus 3 to give minus 81. An alternating geometric sequence is a sequence whose terms are alternately positive and negative. A geometric sequence is also sometimes known as a geometric progression. And now for another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's have a go at part A first. We are required to find the nth and 7th terms of the geometric sequence 2, 6, 18, 54, and so on. So let's solve this. The first term is a equals 2. The common ratio is 6 divided by 2, so the second term divided by the first term. This is equal to 3. Therefore, r is equal to 3. And therefore, the general term un equals a times r to the power n minus 1 is equal to a, which is 2, times r, which is 3, to the power n minus 1. And therefore u subscript n is 2 times 3 to the power n minus 1. We therefore have that u subscript 7 is equal to 2 times 3 to the power 7 minus 1, as shown. Which is equal to 2 times 3 to the power 6. and this equals 1458. And now for part B. We are required to find the nth and 7th terms of the geometric sequence 160, 40, 10, 2.5 and so on. So let's solve this. The first term is 160, so A equals 160. The common ratio, R, is equal to 40 divided by 160. The second term divided by the first term. And so the general term is U subscript n equals A, which is 160, multiplied by R, which is a quarter, raised to the power n minus 1. And therefore, U subscript 7 is equal to 160 times a quarter to the power 7 minus 1. Which equals 5 over 128. And now for another example. Pause the video and have a go. Press play when you're ready to view the solutions. The second term of a geometric sequence is 24, and the fourth term is 72. Find the exact value of the 9th term in the sequence, given that the common ratio is positive. So let's solve this. The nth term of a geometric sequence is A times R to the power n minus 1. So the second term is A times R to the power 2 minus 1, which from our question is equal to 24, and the fourth term is A times R to the 4 minus 1, which is equal to 72, again from the question. So here's the second term with n equals 2 plugged in, and here's the fourth term with n equals 4 plugged in. And as part of the question, we have that the second term is equal to 24, and the fourth term is equal to 72. So we have two equations. A times R equals 24, and A times R cubed equals 72. Therefore, AR cubed over AR equals 72 over 24. And tidying this up, in fact cancelling 1A and 1R, gives us that R squared equals 3. And therefore R equals square root of 3. We can now substitute this into equation 1 in order to help us find the value of A. So this gives us that AR equals A root 3, because of course R is equal to root 3, and from equation 1 we have that AR equals 24. And so we have that A equals 8 root 3. Now we have our values of R and A as shown on the screen. This can now produce the nth term. So the nth term, of course, is AR to the power n minus 1, and we can now plug in the value of A, as shown here, which is 8 root 3, and the value of R, which is root 3. Tidying this up gives us AR to the power n minus 1 equals 8 root 3 to the power n. And so in particular, the ninth term is 8 root 3 to the power 9 minus 1. Of course, here we've substituted n equals 9 into the equation to give us that the ninth term is 8 times 3 to the power 4, which is equal to 648. And now for another example. Pause the video and have a go. Press play when you're ready to view the solutions. In this example, the first three numbers of a geometric sequence with all positive terms are 2, 6 and x plus 12. We are required to find the value of x. So let's solve this. Now the ratio between consecutive terms in a geometric sequence is the same. So for example, u2, which is the second term, divided by u1 equals u3 divided by u2. And therefore, if we substitute in the values of u1, u2 and u3, we have this expression here. So u1 equals 2 has been substituted as shown. u2 has also been substituted, u2 is equal to x, and u3 has also been substituted. If we multiply out this expression and tidy up a little, we obtain x squared equals 2 times x plus 12. Essentially, we've multiplied through by 2x. And this implies that x squared minus 2x minus 24 equals 0. Factorising gives us x minus 6 multiplied by x plus 4 equals 0. And so we have two solutions, either x equals 6 or x equals minus 4. However, we know from the question that the terms are positive. Therefore, x is equal to 6. And now for another example. Pause the video and have a go. Press play when you're ready to view the solutions. So in this example, we're required to write down the first term in the geometric sequence 4, 8, 16, 32 and so on to exceed 500,000. So let's solve this. We're going to begin by trying to specify exactly the nth term of the geometric sequence. The general term is u subscript n equals ar to the power n minus 1 equals 4, which is the value of a, it's the first term, multiplied by r, which is the ratio between consecutive terms, so 8 divided by 4 here, which is equal to 2, raised to the power n minus 1. This equals 2 to the power n plus 1. We require the value of n such that the nth term is greater than 500,000. And of course the nth term is 2 to the power n plus 1. So we need to solve 2 to the power n plus 1 is greater than 500,000. Taking logs gives us this expression here. We can now take the power of 2, which is n plus 1, and multiply that by log 2, as shown in this expression. Rearranging will give us that n is greater than log 500,000 over log 2 minus 1. And this expression is equal to 17.93. Therefore, in particular, n must be greater than 17.93. However, since n has to be a whole number, we can say that n is greater than or equal to 18. In other words, the 18th term is the first one to exceed 500,000. This brings us to the end of this session. If you have understood its contents, you should be able to find the nth term of a geometric sequence. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.